My name's Dave Rowland. I'm the CTO of the Audio Squadron Group. We have two main brands. On the hardware side, we have our Prism Sound brand, where we make high-quality audio interfaces and converters for large studios. And on the Traction side, we make a bunch of synthesizers and our DAW waveform and the open source Traction engine. When I'm not programming, I like to do building work. This is some various stages of garden office I built, and I like to think it's similar to programming in that you're solving engineering problems, but all the tools that you use are different, very physical, and it gets me away from the computer. And it turned out pretty great, and that's where I do my programming every day now. Once I finish with that, I move to the front of the house to learn some new skills like brickwork, pitched roofing, rendering, and built a porch. And that turned out pretty great as well. So if you want to talk to me about something that isn't programming, building work, power tools, I love all that. So there is a plan for today. I'm going to start by showing you a load of talks that you should watch instead of this one. Then we're going to do some comparisons around how safe different languages are and where they get that safety from. And we're going to kind of be skewed a bit towards C++ to see how that might be becoming safer. And hopefully this will all be tied together towards the end, but there will be many tangents. So strap in and hopefully you enjoy the ride. There is a goal. And that's that I want you to start thinking about safety. I think this is a genuinely serious problem that's kind of acted on a bit flippantly in many industries. So hopefully we can kind of be a bit more serious about this. So a good kind of grounding for this is Timur's talk from CPP on C a few years ago called C++ and Safety. And if you haven't watched that, I suggest you stop what you're doing, go and watch it. Hopefully you're back with us, and hopefully no one's going into the corridors now, right? Okay, but definitely watch this. And in this, he posed a question. He said, who cares about safety? And he surveyed a lot of the C++ community and did some analysis and came back with this conclusion. And he said, today, C++ developers generally do not perceive undefined behavior as a business-critical problem. He did follow it up with whether they're right. That's a different question. And I'm going to try and convince you that you should definitely see it as a business-critical problem. And there have been lots of talks on this kind of area over the past few years. I kind of split them into two conceptual and practical categories. The conceptual sort of higher level, philosophical, and then the practical ones give you kind of concrete tips for how to improve safety. And this was kind of all ignited by a bunch of government reports from around the world that said we should be moving away from memory unsafe languages to like C and C++ towards memory safe languages. And because of this, I think that it's entirely possible that in the near future, companies will have to adhere to some form of programming safety regulation. Now, I don't know what that would be. It already happens in industries like automotive, but maybe it's just like large companies have to provide a report for their strategies. But I think we need to start thinking about it. And if we're going to be thinking about it, we should probably know what it is. So here's a kind of rough definition of safety, which focuses on system reliability and proper functioning. For example, preventing crashes in medical devices, which can be harmful. And security introduces this idea of an intentional malicious attacker. So includes things like they will aim to take advantage of safety holes in order to gain access to systems, so hacking, malware, ransomware, that kind of thing. And this can kind of be rephrased slightly a bit more simply to say a safe program is a correctly functioning program that doesn't crash, and a secure program is a program that a malicious attacker can't exploit. And in Timur's talk, he quoted J.F. Bastian. I couldn't find J.F.'s original quote, but he said, no functional safety without security, no security without type, resource, and memory safety. And this kind of starts introducing the idea that all these things are interlinked, and they can kind of be summarized as language safety. And this can be split out into memory safety, which includes type safety to ensure that we're accessing objects that are actually of the type we think they are, bound safety to ensure that we're only accessing memory that has been allocated to a container, lifetime safety to ensure that we're not accessing objects after they've been deleted, and initialization safety to ensure that objects have been fully initialized before we're using. There's also arithmetic safety, which includes things like divide by zero, signed integer overflow, thread safety, which deals to ensure that our code is data race free, and also definition safety, which is basically trying to avoid ODR violations. And Dave Abrahams has spoken about this in relation to his development of the Hylo language. And he has kind of a really terse way of saying this, which is a safe operation cannot cause undefined behavior, and therefore a safe language only has safe operations. So again, I'm going to paraphrase from Timur's talk, where he says, a programming language is safe if it doesn't let you express undefined behavior. So why don't we make all the UB in C++ ill-formed? Well, there's a few good reasons. The first is performance. The compiler can make assumptions about your code that you haven't written any UB in order to optimize well. A high remit for C++ is also backwards compatibility. If you want to compile old code, but now you've defined some new behavior, the program isn't going to function the same probably. And also, defining behavior can also introduce complexity. And we'll see that in some other languages later on. And this can kind of ruin the expressivity of a language. The other thing is portability. C++ is meant to be kind of run everywhere. And if you define some behavior for a specific architecture, it might be impossible or really slow because it has to be implemented in software on another architecture. The way I like to think about this is a kind of pyramid scheme. At the top, you sort of have security with malicious attackers that sits on top of safety holes, which sits on top of language safety, which really sits on top of undefined behavior. So if we can focus our attention on the undefined behavior aspect, we kind of improve everything that above it. Now, I'm going to take all the examples today, assuming that you have either a blank slate or an existing C++ application. Who has no C++ in their code base? Not a single hand. So that's, yeah, we're in a good position. I'm not really talking about kind of research things, so no Python, more if you're creating binaries that are going to run on someone's machine. We're not going to talk about Carbon specifically because it has the same memory strategy kind of long term as Rust, and Rust and Circle are kind of intrinsically linked as well. But before I get talking about the other languages, I just want to give a quick nod to this safe CPP tool. It's a slightly different approach to the other languages we're going to talk about because it aims to create a safe subset of today's C++. And then it provides a new library in order to kind of use a safe version of the library to be used, and then a linter, which is kind of like a static analyzer pass to ensure that only that section of C++ is used. So I'm not a big fan of the language or the code that it forces you to write. It's kind of very verbose, but it's an interesting idea that I think parts of can be used. So we're really going to talk about these 6 languages, and we're going to try and build up a kind of comparison. If you see this green box, you'll know it's like a static or compile time enforced feature. A blue box means that there's a dynamic or runtime checked safety feature. Yellow means there's a solution, but it's an external tool or application. And red means there's essentially no solution for this. Here's where we're going to end up. So I've kind of given the game away a bit, but if we kind of just blur our eyes, we can sort of just see the colors bleed through here. And if you look at today's C++, it's kind of in stark contrast to everything around it. If we look at the more kind of safe versions, we can see there's lots of green and blue, but maybe towards the end of the talk, we can see where we might get improvements to C++. So I'm going to talk about Cmajor first. And the pros of Cmajor are that it's basically completely statically safe or enforced, including bounds, which you don't get with a lot of other languages. There's a little bit of implementation-defined arithmetic behavior, but that's to maximize performance. It's not the same as UB. It will just do whatever the hardware does. So that's divide by 0 or signed integer overflow, that kind of thing. And it does this to be fast. The cons are that it's a DSL, right? It's just for audio processing. So if you're going to ship it as a plugin, you need some additional logic around it, which might be JavaScript, but probably some C++ as well. But the idea is that the code that you're writing is this kind of safe DSL. And because it needs a runtime, you have to kind of bundle that. But there are tools to do this, and they're well tested, so you can kind of trust them. If we contrast that with C++, we can see the first thing is there's lots of tools to catch common errors, right? We have sanitizers and static analyzers, and sometimes compilers can help. They're getting better and better, and they can catch more and more things. The cons are the tools are not default. They often come as separate applications, and they're different across different platforms. They're also often mutually exclusive. So a compile step is different to a static analyzer step, and the sanitizers are different still, and they're often can't be run at the same time, like ASAN and TSAN. And sometimes you can end up with false positives and negatives. They're actually pretty good, but you need to be aware that these things can happen. So the question then becomes, can C++ do better? And there have been lots of talks about this, which are on that YouTube playlist that I mentioned. But one of the best, I think, is Tristan Brindle's talk from CPP on C, Practical Tips for Safer C++. That's online now. It wasn't when I wrote the slides. But in summary, he kind of says this. You can use a modern C++ ranges library, like std ranges, or better still, a Flux library that we'll take a look at. Use hardened standard library modes like libc++'s hardening, debug, and fast, which is designed to catch contract violations, so bounds checking and push on an pop on an empty vector, that kind of thing. And also, these are designed to be run in production, which is interesting. Then for lifetime and initialization, static analyzers are kind of the best tool. And for arithmetic, you can use these saturating operations where they kind of limit your avoid wraparounds, basically, coming in C++26, and I think Flux has these as well. But also, if you're on Clang or GCC, you can use -f trap v, which will insert instructions for to check signed integer overflow, but there is a performance penalty with that. Threads, there's only really TSAN, that's the only game in town. Just a quick word on Flux. It's a cursor-based design, which apparently is similar to Rust iterators. And they're essentially just a number, so an index into a sequence. And because of this, they can't dangle. There's no pointers here, and they can't be invalidated. And the APIs force you into bounds checking. You can opt out of bounds checking if you really need the performance, but you kind of get a lot of safety by default. If we take a look at lifetime safety enforced through static analyzers, this is a classic use after free example in C++. So you allocate an int on the heap, then get a pointer to that, and then the unique pointer goes out scope, destroying the object, and then you use that pointer afterwards. Now, compilers can't really catch this. I tried on quite a few. So you have to run these static analyzer passes, which will go kind of deeper into your code and then spot that this is a use after free issue. The problem with using all these kind of static analyzers and sanitizers is that they require good test coverage. They need code to run on. And the problem with tests are that they generally cover intended use cases. If you do TDD or BDD, you tend to write the code that you expect it to do first. The other half that the tests usually come in is issues that reported either in QA or beta testing, sometimes end users, and then they kind of become regression tests. Fuzzing can help with this, but they're a bit clunky to set up as well. So I want to dig a bit deeper into static analyzers. And the first thing we can see is there's lots of these. Some are commercial, some are non-commercial, some come with compilers, some don't. They have some intersection and some completely individual checks as well. We're going to focus on these kind of two, but mainly the Clang Tidy version of the core guidelines checks. So the core guideline checks in Clang Tidy look like a bunch of rules that start with CPP core guidelines -pro dash, and then the profile that they're checking, and then the individual check. And if we look at one in particular, we can start to kind of see how they're formed. So this bounds constant array index check. I'm not going to read it all out, but what it aims to do is enforce this bounds.to from the C++ core guidelines rules. And it says only index into arrays using constant expressions, pass pointers to single objects only, and keep pointer arithmetic simple. And if you provide the GSL header, which is a non-standard additional library, it can provide a fix-it for you. And this is best illustrated with a code example. So you run Clang Tidy over this, and it will say, well, you've created a static array here, but now you've just got this unknown integer that you're trying to access into this array, which is unsafe. Don't use this. If you know get index is returning a valid index, then you can suppress this with --no lint. But what it's really trying to get you to do is write a safer version of the code using array.app, which is going to throw an exception if it's out of bounds, or the GSL app, which is a contract violation, which by default will terminate, but you can kind of specify a custom handler for that. But the core guidelines can be broad and vague. There's this bounds.for rule, which says don't use standard library functions and types that are not bounds checked. Use the standard library in a type-safe manner. And then sl.con.3, avoid bounds errors. And the reasoning for this is read or write beyond an allocated range of elements typically leads to bad errors, wrong results, crashes, and security violations. So a lot of them basically just say code more betterer. It's a bit unfair, okay? You could cherry pick rules by themselves and they sound a bit meaningless. They do kind of form a coherent framework. But has anyone read the C++ core guidelines? Hands up. Okay, keep your hands up if you've read all 650 pages of them. Right, so this kind of highlights the point. This is the document that is supposed to be the kind of best modern standards that people should be adhering to. And if you've got to know C++, an incredibly complicated language, then read 650 pages of rules and best practice and then apply that in your day-to-day work. It's impossible, even if you're well-versed in it. So warning, this next section is a bit of speculation, so take it with a pinch of salt. There is a kind of ongoing proposal in the committee to kind of standardize some of this static analyzer work. And it's called Safety Profiles, kind of spearheaded by Bjarne and a few other people. The idea here is that you can break safety into these kind of subsections like type, arithmetic, ranges, and so on, and kind of add them as standardized static analyzer checks. So if we take the same example as before, the idea is that you would use this attribute syntax to say enable ranges checks, and then it would give you the same error. And if you want to suppress that, you can do it with some standard syntax. And the rationale behind this, as Herb has been saying in recent years, is that most security or common weakness exploits are just a small subset of issues. So out of bounds write, use after free, out of bounds reads, makes up like 70 to 80% of kind of issues. And if we can fix 90 to 98% of those, we can basically improve safety in the language by 70 to 80%. So it's kind of data-driven, which I think is good. So in summary, they're good because they essentially aim to standardize a lot of this static analyzer passes. And I think the fact that those aren't standard tools is one of the biggest downfalls. So that would be great. And it means we could progressively adopt them. So we're not going to flick a switch and break all of our code. We can add it to new code. We can refactor and add these checks. The cons are, they're a bit of a mess. To be honest, I mean, Timur probably knows more about this. I think this paper's been in flight for about 10 years. It's struggling to gain kind of consensus and get to some finalized version. The syntax has been all over the place as well. There's known difficulties with flow analysis. So there's kind of situations with branching where checks will just kind of fall apart. And there's probably going to be a mixture of compile and runtime violations. And there's even a comment that says in the paper, the initial offering is likely to be a light version. So we're not going to get all of the safety that is kind of possible to start with. So who knows where this will go? And what does it say about threads? Because that concerns me quite a lot. And it basically says, I don't know. It's not completely true. There is a section on concurrency, but it basically says use modern programming practices. Use JThread, use unique pointer, use scope lock. And then there's this comment at the bottom that just says, we need to look at lock-free programming. What does that mean? What are the concrete checks that we should be enforcing? So Herb has kind of taken this data-driven approach and these kind of rules that you can kind of come up with and created a new language called CPP2 that transpiles into C++. And the idea here is that you have safer type, bounds, lifetime initialization, and arithmetic safety by default. So the problem with C++ is you can't break old code, so you kind of have to opt into these things, which is always going to be problematic, especially for learners. So he aims to kind of create this new syntax where all of these things are default. And the idea here is that it can be incrementally opt-in to an existing C++ code base because it transpiles to C++. So what you actually compile into your binary is actually C++ code. And you still have that in the future. So if the project fails or something, you kind of haven't really wasted all your effort. And the other great thing about this is you get perfect C++ interop. There are a few kind of edge cases, but you can use all of existing C++ when you do this. The cons are that it's a different language to learn and teach. There's different kind of paradigms, there's slightly different syntax, but it is quite terse and you can pick it up relatively quickly, like nothing like as complex as C++. It's also still in its infancy, so not battle hardened and we don't know where a lot of the sharp edges are yet. Also, he aims to have improvements in lifetime safety. I've not seen this yet. I know he's got some ideas, but we'll see how they kind of get actually kind of in production. Just a quick mention on modules here, because you'll see this in, definition safety in yellow on pretty much all the C++. Basically, C++ modules will fix this, but they're not exactly rolled out yet, which is why I've got them in yellow. So, and also there's no kind of built-in thread safety to the language either. So kind of switching gears into Swift, a very different language, we can see that as of this year, Swift 6, it's completely memory and thread safe, right? The only things that are runtime checked are bounds and arithmetic, which kind of have to be, but the checks are on by default and you can opt out of them for performance reasons. The cons with Swift are that it's essentially Apple specific. I know it's an open source language, it can be used on any operating system, but Xcode IDE, Swift UI, a lot of the cool stuff is essentially Apple. It's C++ interop, so remember, existing C++ code base is also fairly immature. It's getting better, but it's not like you can just write code side by side today. And with a different language, with different semantics, you also get kind of different results in your code. So imagine this example where you create a vector, create an iterator to that vector, then reassign the vector, and then use that iterator to go through the vector. In Swift, you would get this result, okay? 1, 2, 3, which is the original vector. Now, if we used the Flux library in C++, this is a safe operation, and it's safe in Swift as well, you get a completely different result because you're creating a cursor, which is effectively 0, reassigning the vector, and then iterating through that sequence. And I don't know which is correct here. They're just different semantics. So it's important to realize when you're looking at different languages, what the kind of language semantics give you in terms of results. So we can't really talk about safety without mentioning Rust, because for the past sort of 5 years or so, it's been kind of the gold standard. And like Swift, it's completely memory and thread safe, and almost completely statically enforced, and again has sensible defaults for bounds and arithmetic. It's kind of slightly relaxed in release builds for performance reasons. The cons are that Rust, particularly if you're well-versed in C++, is a completely new language, and it's also a really complex language. There are lots of keywords and annotations that we'll see kind of later on. And this term, fighting the borrow checker, comes up time and time again. I'm going to kind of argue that you can't really get away from this if you want a language like Rust. Swift, you don't tend to have this problem, but you kind of get similar issues. And the other thing is C++ interop with Rust, again, is not great. And Rust aims to introduce most of its safety through this law of exclusivity. And if we contrast a kind of C++ example with how Rust stops us doing things like this, we can see why. So this is the same Flux and Swift example I've got, but in pure C++. So create a vector, create an iterator, reassign the vector, and then use that iterator. So reassigning the vector here to numbers invalidates that iterator, but the compiler is going to, on all warnings, new standards, just going to let you do this and then print out junk. This may look like a contrived example, but pushing back into a vector that's live somewhere else and has an iterator is a really common problem. So I asked Claude, the LLM, to give me a Rust version of this. He said, sure, I can do that. It said it probably won't compile that. It said it will be unsafe. And there's a comment that says, yeah, it's unsafe and it could lead to undefined behavior. And there's a big unsafe keyword in there to let me know as well. But it's essentially, the same thing, and you get the same error. So I said, can you give me a safe version of this? And it said, sure, I can. And it looks really similar to the C++ version, but it doesn't compile. And it doesn't compile because it enforces these lifetime rules. And it says, you've created a borrow, which is kind of like a reference on this line, and then you've reassigned where a live borrow is in existence and then tried to use that borrow later on. You can kind of replace borrow for reference in your head. So this kind of problem just isn't possible in a static language like Rust. So the question becomes, can we add a borrow checker to C++? And some developers on the Chromium project kind of looked into this a few years ago, and they came out with this conclusion, and I'll kind of make this a bit bigger in a sec. They basically said, the language does not lend itself to this, thus memory safety in C++ would need to be achieved through runtime checks. So Sean Baxter is a developer who has a C++ compiler called Circle that aims to be kind of fully standards compliant, but also adds a bunch of extensions to see how the language could be evolved. And he basically said, hold my beer. So he went away for a year or so and added a borrow checker to C++. And about 6 months ago, he kind of announced it to the world. And now if you write this example in Circle, looks exactly the same as the C++ example, you now get effectively the same error as you do in Rust. It says you're trying to use this iterator and this loan has been expired on a couple of lines above it. So it just kind of forces you to not get this problem. And why does the code look exactly the same apart from this stud2? It's because all the complexity hides in the library. So if we look into the vector class, we can see all these weird annotations like T+, unsafe, drop only, the hat is the borrow symbol, and in the mutex class, it's even more complicated because you've got T tilde and then divide by A, things like that. But that's okay, because in C++, we're used to not being able to read the standard library, right? And this isn't specific to Circle. You see the same thing in Rust. You get all these weird annotations to kind of try and propagate lifetime through various classes. The key takeaway is that Circle is safe C++, and more importantly, is statically safe C++. So as I mentioned, Sean kind of announced this to the world with a webinar, and I strongly urge you to go and watch it. Even if you're not interested in Circle, it really kind of helps cement what the problems are and where all the holes are in C++. So how was he able to do this? Well, first of all, he added borrows to C++, which are similar to references, except that you can only have one mutable borrow. You can have any number of const borrows. So you create an object, a size t, you can have multiple const borrows, but as soon as you try and create a mutable borrow, then you get a compile error. Then you add relocation, which is similar to destructive move concept in C++, but basically it means you can transfer lifetime between different objects. So you create boxes, a kind of unique pointer, you can use that, and then if you relocate it to another object, when you try and use the original object, it will say, no, this is now uninitialized, right? Its lifetime has ended. And then you need a choice type, which is kind of like a first-class language variant or sum type. And then you need pattern matching to be able to prove exhaustively that you can check all of the versions of that. Then you need an escape hatch, which is typically the unsafe keyword because certain data structures can't be expressed in safe subsets like linked lists. And you need a new safe standard library, which is why they see this stud2. Then you need protocols, which are similar to type traits, and then to implement sync and send protocols where you get thread safety. So this is easy, right? Well, go and have a look at this paper. It's very long, very well written, but kind of exhaustively goes through why Sean at least thinks we need this level of safety in C++. And how is he able to do this? Well, old Circle was like this. It's a handwritten parser which parses C++ and then generates LLVM IR and then hands that off to LLVM to create, do optimizing and code gen. And what he did was essentially added a new step. He pulled the parser and the LLVM apart and said, right, I'm going to parse the code, generate mid-level IR, where I'm going to do all my borrow checking and lifetime analysis, and then use that to generate, or once all the checks are passed, then generate LLVM IR like I did before. And it's because of this, I don't know how feasible this is going to be in existing compiler tool chains. Like, I don't know, it seems like a lot to ask from big code bases, but they're smart engineers. Maybe they can figure it out. Maybe it's easier than I think. But if we review the safety profile of Circle, we can see that it's essentially the same level of safety as Rust, right? It's almost completely statically enforced. And we've got sensible defaults, which I think is key. So checked bounds and arithmetic. And because this is C++, is incrementally opt-in, you can just turn this on for a single file and still interact with C++, existing C++ code. You might just need to say it's unsafe if you're calling out to unsafe C++. And therefore, you get perfect C++ interrupt, which you can't get in Rust. The cons are that this is a closed source project, right? It's an individual built compiler, which makes it a huge business risk. If Sean decides to just stop making Circle, then what are you going to do with all that Circle code? So certainly a risk there. And I've put this as a con that it's incrementally opt-in as well, but that's really just a statement to say, I don't think there is a silver bullet for C++. There's no compiler switch that you can turn on that's suddenly going to make all your code safe. So we talked about memory safety a lot so far, but what other feature does Circle, Swift, and Rust have in common? And I think that's thread safety. And you get this through two different ways, really. There's sync and send in all of the languages, which is kind of low-level safety, and then there's this higher level in Swift that you get, which we'll kind of touch on in a bit. But this is introduced by two kind of protocols called sync and send. And these are similar to type traits, so kind of things that are checked at compile time. And a sync object can safely be shared between threads, so it can be read and written by two different threads at the same time. And a send object can safely be transferred between threads, so you can kind of move the lifetime from one thread to another. And in Swift, you'll see this with the sendable protocol. And this really introduces the notion of isolation boundaries between potential threads of execution. So objects can only pass this isolation boundary if they conform to the @sendable protocol. This can be inferred in some cases if you have kind of trivially copyable pure value objects. Syncable is a kind of special case of sendable in Swift, e.g. a lock-in resource, which is like a container around an object in a mutex, and every time you access the object, it will lock the mutex. So that's a kind of syncable object, but is a kind of sendable at the same time. There's no explicit syncable keyword. And you see this in Swift code with this @sendable protocol. So this is like really low level. You wouldn't normally do this much in Swift, but this is creating a thread with a block or a closure or a lambda, and the thing that you pass it has to conform to this @sendable protocol. Now in Circle, this is called a marker interface, which is similar to Rust's marker trait, which is kind of similar to a C++ type trait. And again, it can be inferred if a copy can be made, so it has kind of pure value semantics, a borrow that can be shared, so that's like a const t borrow, like reference, but not a mutable borrow, because that means another thread might be accessing at the same time. And Sean kind of spoke about this with an example in his webinar that I kind of used as a jumping off point to think, well, could we do this in C++? Now, I've started working on some ideas. This isn't production code. It's kind of more just a kind of playground experiment. But I started building this up and ended up with a whole bunch of slides that I realized I had no time to talk about. So we're just going to jump towards the end, and hopefully you can kind of just follow it a bit, and it will kind of become clearer when we get to the examples. So the idea here is that you create wrappers around existing C++ constructs like thread, and then you constrain the things that you pass to it. So the arguments need to conform to this @send concept, which we'll see in a second, and the invocable, the callable thing that you pass has to conform to a bunch of other restrictions we'll look at individually. But the main thing is this send concept, which is really this is-send type trait. And there are two parts to this. Firstly, we disallow anything that's an L value reference or a pointer or a lambda, because they can have captures which effectively we can't check. So they could be references or pointers to other objects. So we're kind of trying to avoid passing anything to a thread that is a pointer-like thing. But we will allow things that are move constructible or kind of global function pointers, that's pointers that aren't member function pointers. We try and assert this statically with a bunch of checks, so you can see the things that pass this concept check here, which are essentially just kind of pure trivial objects. This can be kind of summarized as we can't pass between different thread execution contexts L value references, object pointers, or lambdas, because these may be referenced outside the thread boundary, so they can be aliased somewhere. And we're only going to allow R values, because that's C++'s best idea of kind of relocation, and non-member function pointers. And this is the best we can do to kind of ensure that no data is shared between the internal thread execution context. And sync is a slightly different idea that we can kind of build up that essentially starts with everything being false, so no object is sync. There's only one thing in C++ that adheres to this idea of syncable, which is atomic. So you can safely access an atomic on two sides of a thread or on multiple threads safely. And again, we can check this with a bunch of static asserts. So we can add this is sync, a bit like Swift does, to our send protocol. So we can say, well, actually, if we pass anything, even a reference to a sync object between to a different thread, it's still safe to read and write that object. So it kind of does conform to this send protocol. But this doesn't really solve lifetime problems. What we really want to kind of get to is to say, well, what we want is a shared pointer to an object that adheres to the sync concept. So a shared pointer to an atomic would be kind of what we're after. So I kind of tried to rebuild Sean's example with these rules in place and said, what does the compiler kind of force us towards building? And it basically ends up looking a bit like the circle code. So synchronized value is a boost class, and there's a standards proposal that's been around for a long time, but it's essentially that locking resource, so a mutex and an object, and then you have to use this apply function to get a reference to the object whilst the mutex is locked. And we need to make a shared pointer to a synchronized value to this string. Then we can pass it to a bunch of different threads that are running. If we effectively create copies, so convert those into R value references, and then pass on to our thread. So this extends the lifetime of that S because it takes a copy of the shared pointer. And then we can pass this global function pointer, entry point, to our safe thread constructor because it's not a lambda or a member function pointer. Then we kind of have to write our entry point in a way that accepts those objects. So we've got shared pointer to a synchronized value to a string. And then we have to kind of unwrap it by using this apply function to lock the mutex. And then we can safely have multiple threads, append to the string and print it out and so on. So I kind of removed here everything that you would have to write and looked at just the bits of kind of enforced safety that we'd get to see where the problems would lie in C++. And the big kind of first obvious thing is this is only surface level. So we can check the object, but we can't check multiple layers of the object. So if this string was more like a node that has pointers, those could be aliased by anywhere. So we kind of shoot ourselves in the foot with something like that. The other thing is C++ is kind of leaky. So in this lambda here, we can call set global function and just take the reference of the object that's passed to us and store it somewhere else. And then we've kind of ruined any thread safety we've got as well. And the other problem is we don't really write code like this in C++. We want to write something that looks like this. But this highlights a problem and why I don't allow lambdas in this kind of safety subset, which is the this pointer. This is just an object pointer. How do you know that the thread that's running this function isn't also being run by a different thread, right? So this kind of starts to highlight where problems are. So how far have we got by kind of doing this sync and send type trait stuff? Well, we've got a bit safer, but not safe. And that's because we've used an unenforceable safe thread class, right? There's nothing that's going to say you used a thread here instead of safe thread because it's my own code. And we've used a non-standard synchronized value class because that's not standardized either. And because of that, we've had to add our own type trait to say synchronized value is sendable. And we've also done a lot of fighting with the compiler that I, luckily for you, didn't show you. That's a lot of the slides that I had that I tore into fire. And a lot of that comes from template instantiation, which I think is actually kind of similar in spirit to fighting the borrow checker because you're trying to please the checks that the compiler is forcing on you. And the other thing is we've also added a lot of overhead to our code because we've got now atomic reference counting in the shared pointers and we're locking a mutex everywhere. You don't always get these overheads in Rust because you can share borrows, which are essentially just kind of under the hood pointers that are lifetime checked. So we've got a solution that is not bulletproof and it's not beginner friendly and it's certainly not default. So I'm not sure I could describe this as a win. But if we do this kind of comparing C++ with these checks and circle side by side, we can see the code that it tries to kind of get you to write is actually pretty similar. And there's similar concepts here. So first, in the circle code, we're copying the shared data and we have to create a copy in C++ syntax here as well. And then in circle, we have to kind of lock the mutex first and then get a borrow to the object. And you have to use this apply function in mind. So it's similar, but I think the intention is expressed more clearly in circle. So there have been a lot of talks about reflection in C++ just recently in the past few months, really. And I thought, well, maybe this can kind of come to the rescue of these ideas. So remember we had this example where you've kind of got two levels of indirection because you've got pointers inside an object. Maybe we can reflect over all of the objects and check that they all adhere to this syncable protocol or type trait. And this is a similar idea to, I think it was Barry Revzin wrote a paper saying we could implement is trivially, what is it? Right, relocatable. I think it was that anyway. It's basically saying you can write this stuff in using reflection as a library rather than having to make it part of the language. And I think the idea will probably hold up pretty well here. And the other thing is because lambdas are essentially just classes or structs, then we could do the same type of reflection here. They're just unnamed. They're kind of built by the compiler. So this would kind of be rejected as well. And when I started thinking about reflection, I thought, well, maybe we can do some other tricks to try and improve safety. There's kind of obvious stuff that you can create kind of value wrappers around shared objects. So things like juice value and value tree, which are essentially just an API and then a reference counted object internally. You could just write that once and generate that reference counting. And then you could maybe do things like create that copy on write as well. And then I thought, well, can we use this kind of wrapping idea to create thread-safe wrappers? So maybe we can wrap this synchronized value and some other variations as well. And we'll see async classes in a sec. Now, bear in mind, this next set of slides do require C++ 26, and that isn't complete yet. Hopefully, reflection will still be in, as long as it doesn't get torn out. It does rely on code injection, and I'm hoping that's going to be in, we'll see. And I've also used Herb's Metaclasses proposal, just because it's a really nice syntax for what I want to show here, but it's not required. There's another way to spell this. And also, don't get too hung up on the syntax here, because it's probably likely to change a bit. But what we want to do is effectively write this person class, so just a plain person with a getter and setter, and then say, apply this kind of synchronized metaclass to it. And what that's going to do is generate a wrapped version of that class, of that person, and it's going to reflect over effectively each of the function declarations and wrap those in lambdas, and then wrap the person object in a synchronized value. So what we're doing here is effectively locking this person and just forwarding on the arguments into it. And the same when we return this, we're just kind of calling the internal function whilst we're locked and then returning the value that we get out of it. And because we're generating this, if we had this notion of syncable, we could generate the type trait for it now, and then it would kind of just be opt-in to this system automatically. Now, I haven't mentioned any of the reflection because the syntax is a bit kind of gnarly. You just kind of have to trust me that it's doable. If you want to look at it more, Herb talked about this in his CPP Con keynote, and David van der Voort gave a great keynote at the same conference, showing all kinds of different reflection ideas that you can have. But just to kind of build on this a bit more, I thought, well, you probably wouldn't write that kind of thing with a synchronized value. You'd probably just say, I want a mutex version of this, and then you would just add a mutex and then lock it before forwarding on all of your calls. And again, we can add the isSync type trait as well. But maybe you want a kind of more optimized version. Maybe you could use a shared mutex that looks at all your const methods or functions and uses a shared lock, and then maybe in the non-const ones uses a unique lock. So, improvements there. And maybe you want a real-time version of this, because nothing I've talked about or going to talk about is real-time safe. But if you made this a seek lock, for example, then it would be a real-time safe version. So check out Timo's talk if you want to know more about those. That is what you're talking about. So just kind of in review, if we got these kind of wrapped metaclasses, rather than writing this kind of laborious shared pointer to a synchronized value, this could kind of become just a shared pointer to a person because it's already safe. And then we can just get rid of that apply nonsense and say, just set the first name and print it out. And that's now all thread safe. And if we introduce several metaclasses or reflection steps and we kind of wrapped person in a value shared pointer wrapper, we would just have a person here. Now this actually looks very close to Swift code because this is just a person with automatic reference counted semantics like a Swift class. So that's sync and send. And this reflection idea got me thinking about actors, which is the higher level idea of thread safety in Swift. Now, in Swift, you write an actor just by replacing class with actor. And what that effectively does, it takes all internal members and serializes them onto a dispatch queue or a thread. And because these are now kind of asynchronous operations, it forces you to await the result. And I thought, well, can we implement that in C++? So I thought, taking the same person, what if we could write a metaclass or a reflection step called actor? What kind of code would we need to be generated? And it would look a bit like this, I think. So you do the same kind of wrapping as you did before, but now we're going to use the proposed, which I think is in for 26, sender's proposal, and we're going to kind of do the same wrapping that we did before, but now create a sender that is scheduled on a thread pool. And if we only have one thread in that thread pool, any accesses through that thread pool are going to be serialized, which makes them inherently thread safe. Now we have to wait for that result to come back, so we just block and then we can unwrap the value and return. And it's exactly the same when we're setting the first name, we just need to capture the argument that we're passing on to the Lambda. Now, this is a bit of a messy example, but the idea is that the green bar is my kind of main thread, and then the purple is another thread that I'm starting, and you can see that the object accesses are all on this third red thread. So they're kind of all thread safe with respect to each other. And then I thought, well, there's this other idea of coroutines, which are effectively awaitable things. And in the sender's proposal, any sender is implicitly awaitable. So we could write this, rather than blocking, we can just co-await and co-return that and package it into a task, which is effectively a packaged coroutine. And then we could co-await the result of this when we want to finally get the string out. And we can kind of write this really simply here by just co-return, co-await, std_exec, then the scheduler that we want, and then just a lightweight lambda around the function. Now, and you can see this the same thing in the return. You just turn a void task. So the only bit that we're really reflecting on is the function declaration here. And if we look at how this compares to the Swift code, it's basically exactly the same. And you use it in basically exactly the same way. Now, this isn't a full actors implementation. There's other ideas that you could build upon here, like maybe you want something that's always accessed on the UI thread, and you kind of have a dispatch queue that is processed by your UI thread. And there's some other ideas like grouping actors together. So maybe you can return awaitables, kind of chain those up and just process them in one go. But I certainly think it's an interesting idea worth exploring. So in kind of summary, I showed this at the start, but now you can see it in all its glory. I'm going to kind of knock Cmajor off because I think it has its place, but it's a kind of a DSP DSL, and I'm thinking more kind of systems programming languages here. And I'm going to remove Swift for the kind of Apple-centric reasons that I kind of spoke about, although I think we can learn a lot from the language. And I'm going to move Circle to the end. And now you can see sort of this cascading improvement in safety. So this is where we are today on the left-hand side. But maybe in the next sort of, 3 to 6 years, we can improve C++ and maybe introducing some ideas that I kind of talked about today, get to this level of safety. And that's probably good enough for me. So in conclusion, I would say certainly use Cmajor or JavaScript where appropriate, because this minimizes your unsafe area. So for DSP, that kind of thing, I think it's just a really good language for that. For C++ code, help is coming. Like the language is improving for this, and it's going to continue to improve. There's a kind of bunch of best practices, and also use all of these on CI as well. Personally, I'm probably going to start using some CPP too. I think just having the defaults on, safer defaults, I think is a huge win. And it's a lower business risk than something like Circle because we get to keep the C++ code. And who knows, maybe eventually we'll get borrow check C++, but I don't know. Thanks very much.